Very good. So I've made this parameterization of the energy momentum here in terms of some energy scale omega, as well as a pair of complex coordinates, which parameterize the location where some momentum eigenstate lives on the celestial sphere. In addition, we've shown that the bulk Lorentz group is manifested as a boundary conformal group on this two-dimensional celestial sphere, which is the location of our holographic description. In addition, I've defined some conformal primary operators by doing some Mound transform on some annihilation operators in momentum eigenstates. And these conformal primary operators have dimension, which is given by this parameter that appears in the Mound transform, and the spin is related to the bulk helicity of the particle. Celestial amplitudes are therefore defined by doing the Mound transform on all external legs. And these celestial amplitudes, due to the fact that these are conformal primary operators, necessarily need to transform as conformally covariant correlation functions. Okay. In addition, I've defined these so-called conformally soft modes. So when this parameter k is an integer and plus spin, which will be an integer or half integer, depending on the statistics of the particle in the bulk. The upshot is that when you take this conformal dimension here, and then you consider this limit, these operators, they look like they're going to vanish due to the fact that this limit looks vanishing. However, indeed, they're non-vanishing inside correlation functions. And this is due to the fact that these regular conformal primary operators have poles in them at special values of their conformal dimension. So what happens when you insert these conformally soft modes into a correlation function is it picks out a particular term in the soft expansion, which acts on the rest of the correlation function. Now this equation here, this is related to conserved currents for asymptotic symmetries in a very general way. So these conformally soft theorems, irrespective of the particle species, can tell you something about asymptotic symmetries. And finally, they're related to this celestial stress energy tensor. So I'm going to show you some particular conformally soft mode related to soft gravitons. And in fact, this will define the celestial stress energy tensor. Okay, great. So shall we get into it? So I'm going to consider the delta equals 0 conformally soft graviton. Okay. And I'm going to consider the minus helicity graviton. Though as the similar story applies to the plus helicity graviton, this will be dual to the hatted stress energy tensor in the anti-holomorphic sector in the CCFT. But I'll just do the minus helicity graviton for simplicity. Okay. I'm going to insert this thing into some correlation function. And as mentioned previously, what happens when I insert this into some correlation function is it just picks out this term in the soft expansion. And delta equals 0 here picks out the term in the soft expansion, which scales as omega to the power of 0. This is the so-called subleading soft graviton theorem, which we discussed yesterday. And its expression is explicitly known and it's universal. And let me just write it down. What we have here for simplicity, we have okay. And this thing is acting on some celestial amplitude without this conformally soft graviton present. All right. Now let's look at the dimension and spin of this operator. One can read that this operator has dimension delta equals 0. And this is just due to this limiting procedure here. And the spin of this operator is related to the helicity of the minus helicity graviton in the bulk, which is to say it has spin -1. Okay. Oh, sorry, spin -2. What am I talking about? Yeah, sorry, gravitons are spin 2, obviously. And when you translate this data into a pair of H and H bar conformal weights, we find that h is equal to -1 and h bar is equal to +1. Okay, so I'm claiming that somehow this object is related to a usual stress energy tensor in a conformal field theory. And this looks quite bad because a stress energy tensor in a CFT, you may be familiar with this. This has weight h equals 2, h bar equals 0. This is one of the defining features of a stress energy tensor. Okay, so what's going on here? Well, let me give you one definition and perhaps that'll clarify the construction of the celestial stress energy tensor. It's not quite this, but it's related to it. So definition, the shadow transform of some conformal primary operator, I'm just going to label it OH bar, so it'll have weights h and h bar. We define this to be as follows. So I'm going to put a tilde, which references the fact that I'm taking a shadow transform. And it's some integral transform. So n here is some normalization constant, which I'll tell you in a moment. So I'm doing some integral over this complex W plane against this kernel. And the thing I'm integrating is my conformal primary operator over here. Okay. So one can check that this thing transforms with weight 1 minus h bar. Okay. Another definition. The holomorphic stress energy tensor in the CCFT, this TZ thing, this is the shadow of this.
Sorry, is O tilde a primary? No.
It transforms like a conformal primary. Yeah.
It is still a primary.
Yeah. Good. Yeah. All right. So let me write this out rather explicitly. We have TZ is equal to 3 factorial over 2 pi. The numerology here depends on what h and h bar I choose for this normalization constant. d2 omega z minus omega to the 4th O0 graviton. Okay. So this is how I define the stress energy tensor in the celestial CFT. This is just a quick exercise in algebra. Verify that TZ has weight 2, 0. So look at how this integral transforms under a conformal transformation, and also show that it satisfies the Ward identity for a stress energy tensor in a 2D CFT, which is to say TZ inserted in some celestial amplitude, this conformally covariant correlation function. This is the following. Okay. If you've seen a lot of CFT previously, this is a rather famous expression. This is essentially what tells you that T is a stress energy tensor. Okay. And the upshot of this expression is that the stress energy tensor has the following OPE with one of these global conformal primaries that I defined previously. Okay. So this OP is just Z minus ZI squared HI plus Z minus ZI So this is the OP between the stress energy tensor and these global conformal primaries.
So if we start grabbing from operator or general, is it primary or is it ordinary? The ordinary or gradual or zero?
Yeah, this is going to be the conformal primary defined this way.
Primary. So always under the distractive transformation, primary become primary.
Yeah, it'll still transform like a primary.
Is that because that's why you don't have the central term?
I'll explain why we don't have the central term, and maybe it'll be a little clearer in a second. So the upshot from this expression is that we can tell the TO-OPE, and if you studied 2D conformal field theory previously, this is a pretty important expression. However, not only does it imply that O is a global conformal primary, in fact, it implies that it's a Virasoro primary. So having an OPE with the stress energy tensor in this way is the defining feature of what it means to be a Virasoro primary. Okay? And in some sense, that's very good. Yeah.
Where does the central source appears?
You just say, oh, one is another T, right?
Yes. Very good. So it's very good that these OI are Virasoro primary in some sense, because something had to be a Virasoro primary. And this is a pretty natural thing for our Virasoro primaries in the theory. Okay. From this expression, one can indeed show that the central charge is equal to 0. So let me discuss what the central charge in a CFT is. If you look at the TT-OPE, okay, well then it'll have the following general form in a CFT. Yeah. So it'll have a piece that looks very much like this, where H is equal to 2 here, because T is a weight 2, 0 primary, quasi global primary, okay? But in addition, it'll have this term, this central charge over Z to the power 4 term, okay? So if you want to compute the central charge of a CFT, all you need to do is tell me what the stress energy tensor is, and then look at its OPE with itself, and then the coefficient of the Z to the power 4 term, this tells you what the central charge of the CFT is, okay? However, the upshot is that you could take one of these OIs to be the conformally soft graviton over there, and then you can actually do the shadow transform. And nowhere along doing this set of manipulations do you find a Z to the inverse power 4 here, which means that the central charge of your CFT is necessarily going to be 0.
Yeah, but you said that the OI is a primary. OI is a primary.
That's right.
But then as you mentioned, tensor is quasi-primary.
That's the point. Is that he tried to construct T, but it is just a primary, so C has to be 0.
That's in a C equals 0 theory, the stress energy tensor is also a Virasoro primary. Yeah. Yeah, no, very good. Cool.
It is kind of something like so. The stress tensor comes from the separating soft bottom
Soft graviton.
of graviton.
Yeah.
So they not even the leading.
With the leading soft graviton.
Asymptotically, these were all like super rotations.
Right. Good.
So stress tensor is not related to the super translation.
That's right. That's right.
What was the leading soft graviton operator?
The leading soft graviton, it'll give you some conserved current, and the interpretation of this conserved current, it's conservation of energy momentum at every angle on the celestial sphere, just like how the U1 case is conservation of charge at every angle.
Yeah, thank you.
Yeah, exactly. All right. Any more questions?
Just to confirm again, like, so the space time stress tensor, energy tensor, some ADM stress energy tensor or something doesn't map to the stress.
Yeah. That's something
It's not
that's
like ADM.
totally, yeah.
So what happens if you do also the schedule transform for photon?
Yeah, good. Nothing special happens. I guess in the photon case, you have a wait. Oh, actually, that's actually. Oh, sorry. In the photon case, you have a weight 1,0 thing, and then it gets sent to a weight 0,1 thing. And sorry, this is our J from earlier, and it turns out that the shadow transform of J is related to J bar. So indeed, it swaps J and J bar. Yeah, sorry, I misspoke. Yeah, it does do something important, but
Why do we need shadow? I mean, of course, we can night time, but.
that's good. So I guess here's some intuition. In usual holographic theories, you expect the stress energy tensor of your boundary theory to somehow be related to gravity in the bulk. Okay. Now try and construct some candidate operator, which has something to do with the bulk graviton, but you also want it to have weight 2,0. And basically you just, you could pick delta equals 2, but this doesn't give you much of anything interesting because there's no overleading soft graviton theorem. You can't take something like, so I guess this is kind of the most natural choice. This is, if you want it to be related to a soft graviton, well then, this is the only way you're going to get something that's weight 2,0. Yeah. Great. Next up, I hope to talk about OPEs in the theory. And this is good. I think some difficulty with celestial holography, as was pointed out yesterday, is a lot of results are either known to tree level or non-perturbatively. And when things are only known to tree level, it becomes a little bit strange to, it's not exactly known, what's going to become of this story when you include all loop corrections. And you can't hope to do that at this level just because of the state of the amplitudes program. So this will be a set of ideas that's known completely non-perturbatively, which is good. All these OPs can be defined non-perturbatively. Okay, so
again, just to make sure that all you're doing is you're thinking about the kinematic constraints from the Lorentz group on the S matrix, right? That's really the only starting ingredient you've had anywhere here, right?
Yeah.
So everything is kinematics. There's no dynamics
Yes.
in anything we've discussed so
Good.
far.
Exactly
That
right.
would have been in this structure constant and a 3-point function that depends on deltas and so forth.
Good, exactly right. Yeah, so this has all been kinematics, doing the setup, talking about special operators. Now we're finally ready to talk about OPs and dynamics. Okay. So the idea is that OPEs in CCFT, these are related to the positions of these primary operators becoming close to one another. This is a usual CFT story. To study OPs, you look at when the operators are tending towards one another. So the upshot is that you want to take Zi, which is the position of some operator, to be going close to Zj, which is the position of some other operator. And this will tell you roughly what the OP structure in your CCFT is. But is there a sense in which we can study this from the momentum space perspective? And indeed, Zi going to Zj is precisely the definition of a collinear limit. And these are defined and well studied in momentum space, okay? So the idea is to figure out how OPs work in the CCFT picture. We need to figure out how collinear limits work in momentum space. So let me define that for you. Right? First, I'll give you an example, and then just as yesterday, I'll talk about the general theory of how these things come about. So in this kinematic limit, momentum space amplitudes actually have the following factorization. So in the limit Zij goes to 0, where I define Zij is just the difference Zi and Zj. In the limit where this thing goes to 0 and the particles are becoming collinear, scattering amplitudes behave as follows. So I'm just going to consider some graviton with some spin I, and its momentum is pi. And then there's another graviton which appears in the amplitude with some spin j, and its momentum is pj. And I'm going to be agnostic to all the other particles which appear in the scattering amplitude. Okay? And in this particular limit, the scattering amplitude is given by the following. You sum over k is equal to plus or minus 2. I'll tell you what this is about in a moment. And then you have this so-called collinear splitting function, which depends on the helicities of these gravitons that are becoming collinear, as well as the helicity of this third graviton, which is going to be plus or minus 2. Okay? And this splitting function depends on the momenta pi and pj, which become collinear. And this just multiplies the scattering amplitude with the two gravitons, which are spin si and sj. They fuse into another graviton with spin sk, and its momentum is p1 or pi plus pj. And the other particles that appear in the scattering amplitude, these things in the dots, I'm not tampering with that. Okay? So let me discuss why these collinear limits come about. I'm going to do this Feynman diagrammatically, so this will just be to leading order and perturbation theory, but in this general theory in the next section, I'm going to talk about all this kind of stuff non-perturbatively. Okay? So what's going on here? We're going to consider some Feynman diagram, and there are going to be two external particles with pi and momentum pj. Okay? So you can see from this kinematic description that when I take zi and zj to be very close to one another, remember that zi tells you the direction of the momenta. So when I'm taking them to be close to one another, their directions are lining up. So in this sense, they're becoming collinear. Okay? And if you look at various Feynman diagrams which can contribute to this process, one in particular sticks out, and it's where these two gravitons talk to each other way out here. So they have some interaction vertex out here. They don't couple internally, like pj couples to this external leg. And now this thing necessarily has momentum pk due to momentum conservation at this vertex, where pk is equal to pi plus pj. Okay. And if you look at the propagator for this leg, you see that the propagator goes as 1 over pi dot pj squared. And the upshot is that in this collinear limit, this propagator actually diverges. It goes as 1 over zij. So just as we did when studying soft theorems, when certain things in some Feynman diagram coupled to an external leg, some internal propagator goes on shell. And this tells us about soft theorems. It's a similar story with collinear theorems. So if these two particles talk to each other way out here, then this internal propagator also goes on shell, and it picks up a 1 over zij pole. And this 1 over zij pole will be manifested in the OPEs of the CCFT.
Sorry, but presumably you can prove this singular structure directly from word identities. I don't have to make an argument diagrammatically, or no, it's just only a perturbative statement.
I'll show you a non-perturbative statement in a moment, and it'll be stronger than you'll see, yeah, it'll be quite good. Okay, so note that when we're doing this, we have in mind that z bar ij is actually fixed. Okay, so this seems a little strange. For real momentum, zi or z is related to z bar via complex conjugation. However, what's very common in the amplitudes community is just to continue your momentum to be complexified. And so we're letting zi and zj be unrelated to one another. Okay, so we're working in some complex region of momentum space. And this is a so-called holomorphic collinear limit. Okay, great. So let me tell you what the splitting function is, and one can actually read off what the splitting function is to first level diagrammatically. And we have the following splitting functions. So for three positive helicity objects, the splitting function pi and pj, this is given by minus kappa over 2, where kappa is related to Newton's constant by 32 pi Newton, and then you take the square root of this. Okay. And then you have z bar ij over zij times the following. And now additionally, you have some order zij to the 0 piece, and these things can come about when one of these propagators is coupled to a diagram internally, let's say. Okay, so here's the splitting function of two positive helicity things. There's one more splitting function that one should bear in mind, where a positive and negative helicity thing fuse into a negative helicity thing. And this splitting function is given as follows. You have this minus kappa over 2 as well. You have the z bar ij over zij, same as before. But now this omega business changes slightly. Okay. Plus some order zij to the power 0. Okay. So here are the two splitting functions that are relevant for the gravity case. Okay. So as one is wont to do in celestial CFT, you just have to take a noun transform of these guys, and this will tell you some information about the celestial amplitude. Okay. So let me tell you practically how one takes a noun transform of this. I'm going to do a noun transform over the variables omega I and omega j. And I'm just going to work with the case where I do the splitting function S2, 2, 2. I'm just going to consider this noun transform for convenience. Okay. The first thing I'm going to do is do a change of variables. So I'm going to write omega I is equal to T omega hat. Omega j is equal to 1 minus T omega tilde. Sorry, these are both tildes, not hats. Where we define omega tilde is equal to omega 1 plus omega 2. So this omega tilde is actually going to be the energy parameter of this thing over here. Okay, so that's why it comes about, and you also see these omega I plus omega j's coming down here, which is why it's a convenient thing to do. Note that when you make this change of variables, t lives in the interval 0 to 1. Okay, so yeah.
Can you explain why is it 1 by pi dot pj square? Shouldn't be just 1 by p of pi dot pj?
Oh, sorry. Yeah, good. Yeah, so sorry. Yeah, very good.
And also, even in normal circumstances, it will be 1 by p1 dot pj, right? Because p1 square and pi square and pj square are odd shell.
Yeah.
So why is it why in the collinear limit, why is it special? I don't quite get it.
It's just Zij is going to 0.
Yeah.
Oh, acha.
This is a special limit of the kinematics where the scattering amplitude blows up.
Okay. Oh, I see. Right.
And again, this statement about these splitting functions, at least the leading term is a universal non-perturbative statement, or I'm worried
yeah,
that there's a factor of kappa.
that's right. Yeah, this right here is perturbative, but in the next set of slides, you'll see a whole construction which doesn't involve anything that looks like a Feynman diagram. Okay. Good. Okay, so I do this change of variables in this way.
So just one more thing.
Yeah.
How are these splitting functions actually derived?
This one you can compute perturbatively.
So you take a Feynman diagram and just take this limit and you will see the splitting.
Yes, it's like yesterday. You compute the vertex for this interaction,
Oh,
and then there's also this, and then this part here, the remainder of the amplitude is is this thing. Right?
But it's still a tree level statement. You're not,
Good.
for instance, worried about soft virtual loops.
Yes,
You
exactly,
can
exactly
worry
right, yeah.
about instances that are-
Okay. So when you do this change of variables, you find the following. So now I'm gonna put in the splitting function explicitly. You find minus kappa over 2 z bar ij over zij. You integrate over this t parameter from 0 to 1. Okay. And then you're left with a following non-transform looking thing over this new omega tilde parameter. Okay, so this is just a statement. You do this change of variables, you evaluate the variance Jacobian, and then you take this splitting function, which I wrote earlier, and then you plug all that stuff in. You'll notice, however, that this integral is computed immediately. This is just some beta function. So this is beta of delta I minus 1, delta j minus 1. Okay, so the upshot is that when you look at two Mound transforms of the splitting function, one in each of the variables, then you get one Mound transform in this kind of collective variable, as well as some beta function and this Zij pole. Okay, so what does this mean for the celestial amplitude? Well, we can apply this result immediately to find the following. If we have some positive helicity graviton with weight or dimension delta 1, this is located at z1, z bar 1, and another positive helicity graviton with dimension delta 2, which is located at z2, z bar 2. Well, from our very earliest definition, this is just the Mound transform of the operators in momentum space. Okay, and we have the momentum space operators for the positive helicity gravitons. But I've told you that whenever you put these two things in a scattering amplitude, and then you look at the collinear limit, these things fuse into one more positive helicity graviton related by this splitting function. Okay. So in this Zij goes to 0 limit, you still have these Mound transforms from earlier, and then you have this splitting function times this positive helicity graviton with energy omega tilde. Okay. But I've told you what happens when you do the Mound transform on the splitting function. You just get some beta function times some Mound transform in the omega tilde variables. So the upshot is that this expression is equal to minus kappa over 2 Zij z bar ij times beta delta 1 minus 1 delta 2 minus 1 times this Mound transform over the tilde things with weight delta 1 plus delta 2 times some positive helicity graviton, but we just note that this is exactly the positive helicity graviton conformal primary operator. Something like this. So one can now read off the OPE between two positive helicity gravitons. It's related to yet one more positive helicity graviton times some beta function. And this gives you the singular terms in the OPE. Okay. Is this definition or this construction pretty? Does this make sense?
That operator has a conformal dimension delta 1 plus delta.
Good, very good, yeah. two very quick exercises. The first one is do the same for the splitting function S2 minus 2 minus 2. And this allows you to infer the following OPE. Suppress the Z and Z bar arguments. Okay, so now we know how a plus helicity graviton in the boundary and a minus helicity graviton in the boundary fuse to a minus helicity graviton on the boundary. Okay. The second exercise is convince yourself that there's no splitting function in QED. Okay, so, well, that is to say the splitting function is not singular in Zij. And so of course there's some, but there's no singular terms in the splitting function in QED. And the way you convince yourself of this, at least at some tree level perturbative arguments, is we saw in the gravity case, the splitting function comes from a diagram that looks like this, where this internal line goes on shell, but there's no cubic interaction vertex of photons. Okay. However, there is one for gluon, so one can write similar expressions giving some non-trivial gluon fuses to gluon OPE.
Is it obvious that I have a loop of electrons? I don't get something.
Yeah, it wouldn't have a pole for the same reason the Sock theorems didn't have a pole when you go on an internal line.
Ah, okay.
Yeah.
What does it mean in Fox theory? Here we don't have a scalar. I'm a confused because here Collinear limit.
Yep.
Then you have a singular and you should isolate the Fox theorem. But in QED, does it mean that you don't have a Fox theorem or something?
No, I'd say the collinear limits and soft limits are totally different.
I see.
The sense in which they're the same is, well, if you try and compute something diagrammatically, they usually occur when one of these lines goes on shell. So that's a common feature, but that's pretty much the only common feature.
And one have to think it's just totally different, but similar, looks similar, but different.
Yeah. Yeah.
Can you just say, what is the sphere you're drawing? Is the static amplitude or the CS2?
Oh, sorry. Yeah, this is the scattering amplitude. Yeah. Sorry. Good. Okay. So here we've only studied these so-called holomorphic OPEs, where Z12 is going to 0, but Z12 bar, this is fixed. One could similarly study anti-holomorphic OPEs. This is, well known in the scattering amplitudes literature, and I'll tell you how to talk about such things in a moment.
And the TCG external moment, when it becomes complex, what does it mean? It's just what it is, or?
Yeah, just the amplitudes people they analytically continue all the momenta. So you can think in some complex region of momentum space where things are still on shell, but the momentum isn't real. Yeah. No splitting function means that you won't have when you look at the OPE here, then there won't be something like this. They can't fuse to another photon with some singular term.
There will be some singular term, but
There could be some singular term if you consider some theory where there's a splitting function involving, say, two photons and a graviton. Then they could fuse into a graviton. But they will never fuse into another photon. That loop order.
The one group order they could.
And have a singular term, though. Like there are always these regular terms in the OPE. I'm not precluding that they can have regular terms amongst themselves, but I'm just looking at singular terms.
The question is, could you have not a one over z, but a log z from u? Right, that's still singular, it's less singular.
No, the answer is you cannot, and this will actually be the topic of this next discussion, this full non-perturbative discussion of what's going on here. Okay. Great. So for three particle massless on shell amplitude, the general structure is actually fixed by the following. So first, I'd like for you to note that there's no non-vanishing three particle massless amplitude for real momenta. For real momenta, kinematics demands that all the three particle amplitudes vanish entirely. And this is just because there's no way that you can write some conservation of momentum statement, P1 plus P2 is equal to P3, where all these things are massless. This is just by kinematics. However, in complex momenta, you can. And there are two types of results that you can get. So the most general three particle scattering amplitude in complex momentum is given by the following. So say I'm scattering particles 1, 2, and 3. The scattering amplitude either takes this form, and it takes this form when the sum of the helicities is less than 0. Okay, and what these things are is these are angle brackets. And they appear in the spinor helicity formalism. I'm not going to talk too much about how these things are defined at all. We won't need them. I'm just giving this result so you can kind of see, and if you want to compute these things, then you'll learn the basics of spinor helicity. Okay, but maybe it's worth saying that these angle brackets somehow have these z variables encoded in them. Okay. Now, when the sum of the helicities is greater than 0, you replace the angle brackets by square brackets. And the square brackets are raised to various powers depending on the helicity of the particles. Great. Okay, so these are your two options. It turns out that Lorentz invariance and little group scaling and stuff like this completely fixes a form of the massless three particle amplitude. It's just some coefficient here times this bit of kinematics. So this is what it'll be at all loop order, and in fact, even non-perturbatively. This is your scattering amplitude. Okay, so you can compute these things at tree level. You can compute them at some order in perturbation theory. That's roughly the calculation that's going on over here. But this is a totally non-perturbative result. It'll just be some number. Okay, great. So it turns out that when the sum of the helicities is greater than 0, the holomorphic OPEs are actually going to be non-trivial, while the anti-holomorphic OPEs are going to be trivial. This is just a fact. So if you look at the helicities of these things, then if you take the Zi goes to Zj collinear limit, then the holomorphic OPEs, there's going to be some 1 over Zij term, but there won't be some 1 over Zij bar term. Okay? And vice versa for these. So somehow the helicity of the particles on the boundary tell you whether you got a singular holomorphic or a singular anti-holomorphic OPE. Okay? With this expression, I'm ready to write down the most general holomorphic OPE, and you can do a similar thing for the anti-holomorphic case. So what is the most general holomorphic OPE? I'm going to suppress the Z and Z bar dependence. Yeah. And the singular terms in this OPE go as 1 over Z12, that's this holomorphic singularity. And now I'm going to do this sum over K. What is K? K is the types of particle species that particles 1 and 2 can fuse to. So that is to say, K are the particle species with non-vanishing G12K. So for these ones that are non-vanishing, particles 1 and 2 will be able to fuse to particle species K in the OPE. Okay? And in fact, this 3-point coupling appears explicitly in the OPE. And what multiplies this 3-point coupling? We have a sum from m equals 0 to infinity. What's going on with the sum from m equals 0 to infinity? This accounts for various descendants. So when I wrote down the graviton OPE previously, I didn't talk about descendants, I just talked about how it fuses into the primary operators. This more general expression tells you about all the relations among the descendants as well, and I'll comment on this in a moment. Okay. So you have this 1 over m factorial term, and then you have quite some beta function, which depends on the weights and spins of the various things. Yeah. And what does this beta function multiply? It multiplies z bar 1, 2 raised to the power s1 plus s2 plus sk minus 1 plus m. I know it's quite a beast. Z1 bar to Z12 bar raised to the power. This raised to the power m. This derivative with respect to z bar variables. And then you have the following conformal primary operator, which has these dimensions: O delta 1 plus delta 2 plus S1 plus S2 plus SK minus 2. Okay. One comment I want to make is I put a bar on this conformal primary operator. This bar is related to CPT conjugation in the bulk. So essentially, it flips the spin. So that is to say, if particles 1 and 2 fuse to particle K with spin plus 1/2, then this thing over here is going to be the conformal primary associated to the spin minus 1/2 object. Okay, so that's just something that comes from crossing symmetry and scattering amplitudes. Okay. Great. And this sum over partial bar m takes care of all the descendants. Remember that the global conformal descendants, well, the global conformal descendants in CFT are some object like this. So acting with L minus 1 on O a bunch of times gives you the various descendants. And so all of these partial bars are telling you some information about descendants in the CCFT. Okay. So this is the most general, completely non-perturbative expression that one could get when discussing OPEs in celestial CFT. So just having knowledge of these 3-point functions tells you about all the singular terms that you get in the OPEs. Okay. So a nice exercise is to compute the 3-particle scattering amplitude for a plus helicity graviton, a plus helicity graviton, and a minus helicity graviton. Okay. And this dictates, compute this at tree level, let's say. This dictates the plus helicity graviton uses to minus helicity graviton OPE in the CCFT. Oh, sorry. It fuses to the plus helicity graviton in the CCFT. And why do you have these pluses and minuses? Well, the fact that this is a plus is inherited from the fact that we do a CPT conjugation. of this guy. So this is a minus helicity graviton in the bulk, but we do this CPT conjugation, so it fuses into a plus helicity graviton on the boundary. And similarly, you could find from, again, this 3-point function, what happens when you consider the OPE of a plus helicity graviton and a minus helicity graviton, and it fuses into a minus helicity graviton. And one should check that these are given by, at tree level, the relations that we found with the splitting functions previously. So this all checks out. Cool. All right, now that we have OPEs, we're ready to finally get to some of the really good stuff. This is the symmetry algebra that has been recently noticed in celestial CFT. And appears to be quite an interesting result. So these go by the name holomorphic symmetry algebra. Notice here that if you plug in the spins for the various gravitons, so maybe we'll consider this OPE for simplicity. If you plug in these spins, the beta function actually has poles at delta equals 1, 0, -1, and so on. So, of course, this is not surprising given what we talked about yesterday, how these special values of the conformal dimension at integers are related to conformally soft theorems, and scattering amplitudes have poles. This is just a manifestation of that. So that's heartening to see. Okay. Now I'm going to define the conformally soft graviton modes at all these deltas, all these negative integers. Previously, we've just studied the delta equals 1, which is related to supertranslation case, and the delta equals 0, which is related to the stress energy tensor case. But I'm going to define these operators HK. Okay. So these are just the conformally soft gravitons when you dial their dimension to K. It's literally the same definition as what I have here, this hatted thing, but in the literature they're called H instead of O hat. So to be consistent with them, when you see these objects, you'll know. Okay, and you can similarly define H bars for the minus helicity objects, but I won't need to do that here. Okay. So great. Because there are poles here, we're going to study the operators at these poles. Essentially, we're extracting the residues. Okay. And one can read off immediately that the conformal weights HH bar, they're given by K plus 2 over 2 K minus 2 over 2. Okay. Now what we can do is we can take the OPE for two conformally soft gravitons. So we look at this expression, we plug in the various values of delta, which is going to some integer K, and we plug in S2, SK, and S1. All these things are equal to +2. We're going to be only working with the positive helicity objects, okay? And we look at this expression for the graviton OPE, and then we take this limit, and we find that the H's have the following OPE.
So why are you looking? I thought SK was summing over, right? But this is right.
Yep.
Delta and S of 1 and 2 are the two guys that you're colliding, but then presumably I get a whole host of things on the other side of the OPE.
Yeah.
You're just picking out one particular term in there.
Yeah. So let me perhaps explain that better. In a gravity theory, you'll always get the +2 thing for K. In some other theories, you could get other stuff as well. And this will give you some other symmetry algebra, of which what I'm going to talk about is a subalgebra. Maybe that's, you'll always have the following OPEs, and you might have an enhanced symmetry algebra, but I'll just talk to you about the one that you get when you just consider gravity by itself. Yeah. So we find the following OPE. HK with HK prime, the singular terms in this OPE are minus kappa over 2 1 over Z12. And then you have the following sum. This sum is kind of like the sum over M, but now it's truncated due to the fact that the beta function only has poles at a certain place. And when we're taking the limit of this thing going to 0, you only pick up those poles. Okay. So here's the OPE that you get. This is just a little bit of a mathematical exercise. You look at, what happens to the beta function near the poles. You pick up some various residues. You take some limits. No big deal. This kappa over here, it looks like the tree level result, but I can define it non-perturbatively in terms of this G thing that we saw earlier. Okay, so I'll just call this kappa. Okay. Now, the next thing that we do is we consider a mode expansion of this HK operator. So HK implicitly depends on Z and Z bar. However, we may consider the following mode expansion. We define these operators HKN, which only depend on Z, and all the Z bar dependence is kept in here. Okay. Now, why do we have these various limits? Well, you can recognize that this is just related to the H bar weight. So it turns out that this is a consistent way to do your mode expansion here. It gives you some finite dimensional representation of the anti-holomorphic SL2R. Anyway, it's a bit technical, but this is a very fair thing to do. And the upshot is that each of these are currents. So they depend on Z, but they don't depend on Z bar. And their conformal weight is H is equal to K plus 2 over 2. Okay. So now what I can do is I can plug this expansion into this OPE, and I'll save you the trouble, but this is something that we can do, and this is going to be an intermediate ingredient in the next calculation.
Hey, just a minute. I just want to know, how did you get this general expression, right?
This is the result of a rather important paper in the field. So it'll be hard to succinctly summarize, but essentially you use some amplitudes technology.
Okay. In the usual CFT, this is obtained using the state operator correspondence and things like that, using those kind of arguments.
Finding OPEs?
Yes. So,
OP is done by, this is the usual inserting a complete set of states, right?
yeah, right. So it's just the same usual story.
Yeah, it's the same OPEs that you would get in a general CFT. I guess, yeah. They're derived using momentum space tricks, but yeah, when I say OPEs, you should just think of regular OPEs that you would see in a generic CFT.
But the point is that when you're making these non-perturbative statements, but it's non-perturbative statements in regimes where everything is completely fixed by kinematics again, right?
Yeah.
Because 3-point amplitudes for massless fields, as we know, right, there's no dynamics in it, right? It is, as you said, completely fixed by kinematics.
Up to these G123s.
Sure, right, but
Yeah.
those are, that's like saying the 3-point function, right? The 3-point function has some structure constants, and that's it. But dynamics is in a 4-point function, right?
I mean,
Maybe this
I don't know.
is-
the 3-point functions are kind of the 3-point functions are kind of the crucial ingredients in scattering amplitudes, like especially in complex momentum. Yeah. And at the end of the day, in the CCFT example, like the OPE coefficients are all the dynamics, right? So I think you're getting something pretty non-trivial here from the collinear limits.
But it's not something new. I could have just thought about this from an amplitudes perspective and thought about taking collinear limits there. Is this just a different language for it, or?
Yeah, that's right. This is just a different language for it. This whole set of lectures is primarily going to be starting with what the amplitudes people tell us, and then seeing what we can learn about the CCFT. There's this whole enterprise of trying to find CCFTs from top down, but this is a rather more difficult thing. So I'm just going to explain to you a little bit more about the space of CCFTs and the general structure that we expect. And then, you know, I guess perhaps that's where the research frontier is, and maybe maybe this will give you some insight into how to think about CCFTs from the top down as well, which would be a very exciting thing to solve.
Can you say anything about some convergence?
Of the OPE?
Yeah, also we don't have that one.
Yeah, let's see. Ooh. Yes, so in a regular CFT, you'd expect the OPs to converge in some region before your next operator insertion. And I guess you're asking whether such a thing is true here, right?
I guess the question is that usual argument about convergence, does it require an argument about unitarity giving you a bound on operator dimensions, right? Because here you've completely thrown all this out the window. You have no notion of a bound on operator dimensions.
Mhm.
And I don't know if the usual convergence arguments need that or not.
I mean, this argument usually follows from some path integral argument and some state operator correspondence type thing. I'm not sure if this expansion only converges at a point, which it certainly converges at a point, but does it converge in a neighborhood of that point? The reason that it converges at a point is because in momentum space, you can look at the OPE as well. You know, there's an OPE for operators of the bulk theory, which converges at a point, but some region around that point, I'm not sure.
When Z1 and Z2 are really separated.
Mhm.
So we will have some fractions here.
Yeah, that's right. Yeah, you'll have some regular terms.
So that's somehow different.
Well, CFT OPs also have regular terms as well, right? Yeah, they all have some infinite set of regular terms. However, when you write down the OP, you normally just write down the singular terms. That's this squiggle. This means modulo regular terms. Yeah. All right. Next up. So we have these holomorphic objects, these currents, HKN. I'm going to define one more notion from 2D CFT. We define the commutator.
Can I just?
Yeah.
So the collinear, you could also have like higher point amplitudes or two external particles are collinear, right?
Yes.
And they wouldn't have any singular terms.
No, they would. Yeah. Like from some splitting function or whatever.
Right now, like, so you wouldn't have like products of operators in this operator OP. Like there's an OP limit in CS2, which is collinear limit to the bulk, but then it could also shower to higher point, multiple external particles, soft particles of operators.
That's right.
That correspondingly shouldn't there be like
Well, so I guess in the usual CFT story, if you had O1 and O2 sitting in a correlation function, and you know how O1 and O2 fuse, maybe they fuse into OK. Well, then you literally you can just put this inside the correlation function. And this is kind of the question about higher point amplitudes in momentum space.
I'm asking for the like in the OP itself there are no higher operator.
What would be meant by a higher operator?
You mean not a primary or?
Like an O times O, but a different questions in the.
Yeah, something that's not a primary, right? You can take normal order to a square, right? That's not a primary, but it's a valid operator, but then you just have to use the normal game of reducing this by pulling out the normal ordering. But I don't think,
Yeah.
We were trying to just ask, like, there are in this finite city formats, you also have non-perturbative statements for multiple endpoint amplitudes, right? And this MHP case and so on.
Okay, yeah.
So, if you take a collinear limit of this, in this MHP amplitudes, if you get to make a bigger statement on those,
No.
or they are not similar, or
If you just think about MHV stuff, you would learn some regular terms in the OPE.
well, the singular terms such as this.
Yeah.
They all come from three-point amplitudes. Okay.
We define the commutator of two holomorphic objects. I'm just going to call them AZ and BZ. You define their commutator via the contour integral. Okay, so this is just some definition from usual CFT. I won't go too much into explaining why this is a good thing to do, but it's in the classic books. Okay. Now, using this definition, one may compute the commutator of HKN and H A prime N prime. Okay. And this is some deeply complicated expression. It's like horrible. It involves, and let me count here, 6 factorials and then a prefactor. It's a mess. So it's a horrible thing times HK plus K prime N plus N prime. And I'll spare you the misery of writing this. And the reason I'll spare you the misery is because I can write a new set of operators, some redefined set of generators, for which this expression looks a lot simpler.
Can you just quickly explain how is that definition anti-symmetric in that commutator definition?
because there's an order to define.
That's, yeah, these
No,
things
but
are radially
you
ordered.
exchange A and B, that side will just become B Z prime.
No, if I fix B and I take A around it counterclockwise, that's equivalent to fixing A and taking B around it clockwise, right? Which
That
flips
would
the sign of
require,
the
that
integral.
would require 2 integrations, right?
No. It's just a change of coordinates, right? This whole thing is different, right? I can also, if you really want to think about exchanging them, right? A commutator is really about exchanging the two particles, but in one coordinate system, exchanging it is the same as looping one around the other entirely.
Good. Okay. Okay, definition. We define the W1 plus infinity generators. These are defined as follows. WPN is equal to is equal to 1 over kappa times the following gamma functions. And the reason we're doing this definition is in service of making this horrible thing palatable, okay? And we find that based on the range of what superscripts are allowed here, recall that these superscripts K run over 1, 0, -1, so forth. We find that the range is as follows. P runs from 1 to infinity in half integer steps. Okay? And moreover, there's a restriction on the allowed values of n. And this restriction on the allowed values of n follows from my mode expansion over here. So what values of n are we allowed? N can live between 1 minus p and p minus 1. And this is so-called the wedge. So at the end of the day, we're going to get a W1 plus infinity algebra, and these have been studied, but in fact, we'll only get the so-called wedge subalgebra of W1 plus infinity. this is a technical math term, which means something to mathematicians and real serious CFT people, but anyway, I'll just write down what it means. This is just some jargon. Okay. So the whole point of this, yeah,
This wedge is analogous to just taking the global subgroup of Virasoro, right? You found some subalgebra that closes instead of generating full Virasoro, you can take
Yeah, that's
0,
right.
1 and minus. This is really just that,
Yeah.
morally the same thing.
that's right. It's just some subalgebra of W1 plus infinity.
What is the T relates to the one dimension?
Yeah, so let's see. E is equal to minus, oh, sorry. From here, we see that K, which is the conformal dimension, is equal to minus 2P plus 4. So P is equal to, right? Unless I did my algebra wrong, which is always felt like, no, it is wrong. I think. Up to some algebra errors. This has become too complicated for me.
So the lowest one is start.
No, the lowest one starts from when you put in delta equals 1. Oh, Yeah.
One.
yeah.
And then for.
Good. Exactly. Yeah. So indeed, as pointed out here, you have poles only at these values. However, your first W generator has conformal dimension equal to 2. This is something you can do, but you'll see it ends up being a rather trivial thing. Like if you look at the W1 plus infinity algebra, when you put in P equals 1, let me just double check this. Yeah, when you put in P equals 1, it's just a central term of the algebra, which is corresponding to the fact that at delta equals 0, there's no singular terms. Or delta equals 2, there's no singular terms.
At the P equal to 2 equal, I mean, P equal 2 is just like a 0 and the P.
Yeah.
Is like a 3 plus 1 to the minus 2 or something. You have negative one or.
Yeah, exactly. The conformal dimensions get negative.
Oh.
Yeah.
It's infinite.
Yeah, it's infinite on the negative side. Yeah, sorry about that. Okay.
We call it usually the double algebra.
Well, we'll call this the W algebra.
Let's see, I mean, I will confuse you. Yeah.
What's the commutator for the W? I guess that's what we need.
Yes.
There's something, I'll have to do some shadow transformations.
No shadows.
Okay. And I mean, very lively, like when you have, I mean, as you want tensor, compartment 2, W
That's
3, 3, W 4, 4, but here it's more like going to the negative.
Exactly.
And this one, just something else.
So indeed, there is a Virasoro subalgebra of W, but it's not the you can, it's not the same as the one we had that was generated by the shadow thing. Yeah. Okay. So this is the full symmetry algebra of conformally soft gravitational modes in CCFT. Let me circle back to your earlier question. What happens when we're doing this sum over K and we include things that aren't just gravitons? Well, at the very end of the day, we'll have things that appear on the right. So say some graviton couples to some other field, maybe a scalar or something like this. Then we'll have an additional term in this symmetry algebra, which tells you about scalars. Okay. So in the non-abelian gauge theory, remember we had this exercise that basically said that in the abelian gauge theory, this thing is going to be 0 because there's no OPE. In the non-abelian gauge theory, you have the so-called S algebra.
This previous statement, like.
Yeah.
Did you also want the scalar to go massless to show them?
Yeah, that's right. Yeah. So this is the so-called wedge subalgebra of the S algebra. Where A, B, and C are color indices and F, A, B, C is just the structure constants. Okay. So one maybe final remark, I also have bonus material, but one final essential remark is that each of these WPNs, well, they depend on some Z, they're all currents on the celestial sphere. And so each of these W generators actually generates conservation laws in the sense that we talked about with asymptotic symmetries yesterday. And these are actually exotic symmetries of nature, which nobody knew about previous to the celestial holography program. However, recasting things in this way makes it totally manifest what's going on, I would say. You know, you have some conformally soft gravitons, you do some mode expansions and it's all algebra, but this is the symmetry that lives in your theory. So all these gravitational theories have this W symmetry, which is kind of totally obvious from the perspective of CCFT, although in momentum space, you would have never guessed that all these theories of gravity have this rich and exotic symmetry structure. Okay. So already CCFT has told us something about bulk physics, which is pretty interesting. And I guess the open question for the future is what more can be learned. So maybe we can take questions, and I also have the bonus material if you'd like for me to get straight into that.
If you forget about the what do you call it, the amplitude side and just look at the WCFT, we can use the same procedure to generate these kind of algebra in any 2D CFT, right? Or is it?
Yes, yeah. So if you have a bunch of currents in a 2D CFT, it defines an algebra via this commutator.
Right. So there, in that setting, this doesn't have any interpretation. It's just that they're just currents. And
yeah, they're just currents. Here's their algebra.
And this was not known before.
No, not even close. Yeah. People are working on finding what this means in the bulk. This is very much an open problem. There's some folks at Harvard who I know are working on this, but it's unpublished right now. So.
Sorry, you said if I have gravity coupled to some matter sector, I don't just have this algebra, right? And it's not even a subalgebra. There's additional terms in this commutator.
That's right. I might have misspoke when I said subalgebra. I mean deformed algebra, rather. That's completely my bad. It's a deformed W1 plus infinity algebra. Something like this. Yeah, that's quite right.
But presumably then, the point is that here, everything we started with was the graviton 3-point function.
Yeah.
And so you say, okay, this is kinematically constrained,
Mhm.
and so I have to have exactly this. And so if I have any other matter, I don't know a non-perturbative result for the 3-point function. So you don't have any exact results for what this deforms to, right? Maybe only perturbatively, or
No, you do know the non-perturbative result because the 3 particle amplitudes are completely fixed. So it'll have some new coefficient.
it'll depend on these fusion coefficients, right?
That's right. Yeah, that's right. But the fusion coefficients are just some numbers, right? So, and in fact, to define these W generators, I've divided by the 3-point coefficients. So it'll still give you some algebra. No.
So for instance, if I think about Yang-Mills plus gravity.
Yeah, good. Yeah, this has been done. There's some classic paper by Andy Strominger, maybe I don't want to say the year, but it was very recently where he does this whole W1 plus infinity story with Yang-Mills coupled to gravity and all these things. And since then it's been generalized to name your favorite theory. This whole structure totally works out for them. There's some paper W1 plus infinity for all spins. Which talks about what happens when you have various massless particles with different spins. How do these algebras get deformed? Blah blah blah. This is like yeah.
I'm so confused about why we're willing to talk about groups, because I mean,
Of course, physically you don't have external gluon states, right? In actual theory, glue confines. There are not these massless glue states.
That's right.
So
Yeah.
it seems like I could never actually say anything meaningful about QCD, except maybe it's a conformal window or something. But
Or you just look at the high energy limit. Where it's deconfined. Where
the high energy limit is the weakly coupled limit, and then I can just do perturbation theory, right?
that's quite right.
So if I wanted to learn some non-perturbative physics, this seems like, is there an idea of how I would use this to really approach? I guess, let me ask the question a different way. If I want to then include heavy states as well,
Yes,
is it a deformation of this algebra, or those are just, they're always at I plus, and so what happens to them in the language of this algebra?
that's a great question. Massless things in their OPEs, to my knowledge, haven't really been considered in CCFT at all for a very technical amplitudes reason. One way that you can see why it might be a problem to have massive things is because a massive thing can never be collinear with a massless thing. Okay, so this is a bit of a problem. And so figuring out what's meant by OPEs and some non-perturbative amplitudes results that tell you what happens when there are massive things, this is still very much an open question. Yeah. And as for the other question about like energy scales of QCD or of pure Bluth or Yang Mills rather, and whether it's confining or deconfining, this is another open topic in celestial holography. Somehow you're doing an integral over all energies. Every time I take a Malin transform implicitly, I'm allowing omega to be, it ranges over all energies. So it looks like at some energies, Yang Mills is confining, some it's not confining. It's a little difficult to make sense of what's going on in celestial holography when your bulk thing is kind of an effective theory. Okay, so in string theory, you don't worry about things like there's some statement about UV softness and things become a lot easier in string theory. But in effective field theory, what's meant by celestial holography is still a little, it's uncertain. Yeah.
But there are these 2D models that are exactly solvable that exhibit confinement. Presumably then you could, yes, the 2D structure is different from the celestial sphere. But I can still try to play the game, right? You
absolutely could, and I encourage you to. I mean, there's been two papers on 2D CCFT, and I think it's a rich playground for exactly the reasons that you said. In 2D, a lot of what's going on in momentum space is known quite a bit better. Yeah. So I mean, a great project is to pick your favorite 2D QFT where you know something about the structure of its amplitudes, do all this Malin transforms, you get some numbers, and then you say, well, what theory lives on the boundary? What theory generates these numbers? What zero-dimensional theory can you write, some matrix integral of, or something that looks like OPEs, and that's very much an open and I think would be a very cool problem.
So you said this collinear is different from the celestial and soft zero, etc.
Yeah.
So this W is results from is collinear.
Exactly. Yeah, all this comes from Collinear, but we see some relics of how these things are interpreted in terms of conformally soft things, which are related to soft things, I guess.
So still the CCFT, which appear in the soft theorem, still also have this W.
Yeah, good.
Yeah. Probably someone already asked, but maybe I missed, but this component dimension is infinity delta. And here delta.
Yeah. Yeah.
And can we call it OP? Like the OP, this delta can appear in the OP of a vector. So is there any problem like OP expansion or
That is the question we're asking about convergence of the OP, right? Indeed,
so
the fact that H isn't bounded by 1 or whatever it is, or the delta has to be bigger than 1, right? So there's a unitary bound, and so you might worry that if I think about convergence, if I have a sum over arbitrarily negative deltas in an OPE, it could conceivably not converge.
Yeah, I agree. It's definitely not unitary. And no, I agree. It's a very weird structure that you see in CCFT with the spectrum. But also all like regular CFTs, their spectrum is unbounded from above. So I don't know, maybe you reckon the same kind of problems.
But I don't know, unbounded from above is fine. It's unbounded from below, right?
Yeah,
Then
that would
get
give you
positive
non-unitary.
powers of, you get infinite positive powers of Z, and so this might not converge, right? Or it converges only at a point, right? You need it to, you really want to converge in a disk where the it converges up until you hit your next operator. And start
That's right.
getting some gradient quantization. I don't know, we have to find the yellow book and it'll tell us what the rules are for convergence.
Yeah, that's right. And normally in a regular CFT, you get infinite powers of z as well in the regular terms.
Yeah.
Yeah, so again, yeah, no, it's good.
I don't think that we discussed convergence. Yeah, convergence.
I don't remember it either.
So,
There's only so much you can put in a million pages.
everything else is.
I don't think I have time for the bonus material, but I don't know. Up to the organizers. I'm just like, yeah, you can have some time. Oh, okay. Well, yeah, feel free to walk out. I know, I know you're, you know, I don't want to keep you forever. I can talk about either constraints from Poincare symmetry on the 3 particle celestial amplitude. So this will give you some non-perturbative structure that you get there. Or the other thing I can talk about is these so-called conformal primary wave functions, which appear in the literature as well. So,
Do the first one.
oh, right, first one it is. I love that. Okay. Here we go. And I'll try and be quick as I can. Okay. So the translation generators act on massless particles as weight shifting oscillators. So what's going on here? Well, we know how the translation generator acts on a momentum space particle. But because all these p mu's, they have a factor of omega in them. They look like omega p hat mu. When I take the Mountain transform of this in the conformal primary basis, these momentum generators look like weight shifting operators in the sense that p mu sends the conformal primary operator of dimension delta to this object. Okay. So this is the case for massless particles. And the upshot is that for massless scattering, we have the following constraint from momentum conservation of the scattering amplitude in momentum space. So here's some n particle scattering amplitude. The sum of momenta must be 0, which implies that at the level of celestial amplitudes, if you consider some amplitude where you do this various weight shifting, this must also be equal to 0. So the sum of these celestial amplitudes in precisely this way, where you first weight shift delta 1 and then you weight shift delta 2, so on. This must be 0, and this just follows from momentum conservation. Okay. For massive particles, the story is a little bit more complicated how these p mu's act. Okay. How they act on a scalar is as follows. This is equal to the mass of the scalar divided by 2 times this following. It's a rather horrible thing, so maybe let me just write for a moment. I know it's like everyone's favorite expression. Okay, this is all multiplied by e to the minus partial delta, which weight shifts everything down by a conformal dimension. Okay, so this is how the momentum operator acts on a conformal primary scalar. If you have a spinning particle in your conformal field theory, it's somehow even worse. However, the expressions are known, so you can just write these things down. Okay. How is this expression determined? One, you demand that p squared is equal to minus m squared. Okay, so this satisfies that relation. Two, you demand that it satisfies the Poincare algebra. So these p's commute amongst themselves. And moreover, m mu nu and p rho have the following commutator. Okay. So the upshot is that by demanding these various things, and you know how m mu nu acts on these conformal primary operators, by demanding these things, this actually uniquely fixes this form.
Can we write PVU in terms of those L's, which you once defined, I think, in the first lecture?
No. No. The L's are related to these m mu nus,
Oh, okay.
right? These are part of the Virasor algebra. When you put P in there, it gives you some larger algebra. Yeah. Now we're going to go back to the case introduced in the very first lecture, where we have a celestial amplitude with two massless particles and one massive particle. And the point is to compare it to the results in this first lecture. So we demand that there is momentum conservation of the celestial amplitude. Yeah. So this M denotes that we're working. Why do I have hold on this? This M denotes that we're working with a massive particle. This P3 corresponds to a massive particle. Okay. In the case where they're all massless, we have this type of constraint. But in the case where one of them is massive, we have a different result. Okay. So first off, we'll note that global conformal invariance fixes the form of the celestial amplitude to look like this. So we have these 3-point structure constants, and global conformal invariance just fixes the denominator to look something like this. This is the general structure that you expect to see in a CFT. Okay, and this is in fact this Z dependence that we found last time. Okay. Now what you're going to do is you're going to take these momentum generators, and they're either going to look like this for a massless particle, or like this for a massive particle, and you're just going to apply them to this result. And you find the following recursion relations. For delta 3 minus 1, C delta 1, delta 2 plus 1, delta 3 plus M, delta 3 minus 1 minus delta 1, 2, C delta 1, delta 2, delta 3 minus 1 equals 0. And in fact, there are two more recursion relations. The next one swaps the role of delta 1 and delta 2. Okay, so it looks just like this, but instead of doing something like delta 2 plus 1, I do delta 1 plus 1. And similarly, instead of delta 1, 2, I have delta 2, 1, where delta 1, 2 is just delta 1 minus delta 2. Great. And then there's one final recursion relation, which reads as follows. Delta 1, 2 squared over 4 minus delta 3 minus 1, all this squared, divided by 4. C delta 1, delta 2, delta 3. And then to this you add the mass times delta 3 minus 1 plus delta 1, 2, C delta 1, delta 2, delta 3 minus 1 is equal to 0. Okay, so here are some recursion relations that you get. You get these three, and it's worth noting that this is a totally non-perturbative result. This is all fixed by conformal invariance in the boundary theory, which is to say Lorentz invariance in the bulk theory. And now we have these recursion relations among the 3-point coefficients.
Yeah, also I have one more question. Why, when we put m equal to 0, why doesn't it reduce to that massless space, that expression?
Let's see. It secretly might, because we had a different momentum parameterization for the massive particle.
But you just have a p hat, we have already isolated that.
No, the p hat still has,
A y.
yeah, it'll still have a y and stuff like this in there.
Yeah, something like that. So we are assuming the OP coefficients are analytic in delta.
Yeah.
Is that an issue in CFT?
Well, no, certainly not in a usual CFT, because a usual CFT has a discrete spectrum. So you would never assume
So why did we do that here?
that they're analyticity in delta seems to follow from analyticity of like energy momentum.
You just look at the definition of the Mellon transform, right? I don't think of this as an OPE, but the definition of O delta is explicitly holomorphic in delta, because it just showed up as this omega to the delta in the integral transform. So it's easy to just continue this.
Okay. So you have these recursion relations, and the final thing I want to say is that these recursion relations are uniquely fixed as follows: C delta 1, delta 2, delta 3. This is equal to some beta function, delta 1 minus delta 2 plus delta 3. All of this is over 2. Times delta 1, delta 2, delta 3. So we note that we have this beta function. We saw this last time. Now I'm going to tell you something non-trivial about d delta 1, delta 2, delta 3, because right now this is pretty trivial. Such that d delta 1, delta 2, delta 3 satisfies the following periodicity conditions. So this is equal to d delta 1, delta 2, delta 3 plus 2. So it's periodic with period 2 and delta 3. Moreover, it's equal to this thing. And finally, it's equal to this thing as well. I'll move away from the board in a moment. All right, so there's 3 periodicity constraints related, on these 3 delta things, okay? So again, this is all orders in perturbation theory and completely non-perturbative. And it seems, my view on this subject is that although the Mellon transform apparatus seems it seems like you're putting in a lot of work on scattering amplitudes in momentum space. The conformal symmetry and things like this, they really fix what's going on quite strongly. So if you imagine all the possible 3 particle amplitudes that you could consider in momentum space, and now you just imagine this, this looks, in my opinion, quite a bit more constrained. You just have this structure constant that appears here, the structure constant, some beta function, and then there's some periodic things that go over here. Formally, they're kind of the same as saying scattering amplitudes in momentum space are Lorentz and Poincaré invariant. That's true. Formally, they're saying the same thing, but this seems quite a bit more suggestive. And this has something to do with the space of 2D CFTs being a lot more constrained and easier to study than the space of 4D quantum field theories. So I think that's one of the reasons that celestial CFT is a pretty promising field. You can hope to study things from this more constrained perspective of 2D CFTs and bring in some 2D CFT intuition to help you along the way.
So usual CFT, all these OP questions you try to impose crossing, and that can sort of that's the step slogan that you in the crossing.
Yeah, all the regular terms. That's right. Yeah.
In the crossing, you get to know more lot about the dimensions and OP questions and so on.
That's right, yeah.
Here we start from an amplitude, so probably is crossing a very trivial statement here, or is it, it doesn't give it to you, or?
Yeah, it's either very trivial, pretty hard. Unfortunately, this is kind of an open question. It has to do with the fact that in momentum space, taking consecutive collinear limits don't always commute. And this will tell you something about crossing symmetry among the OPEs. This actually boils down to an issue in momentum space, and this is also the frontier of something that's being worked on. Yeah, it's very, I mean, one would hope that there's crossing is kind of trivial just due to momentum space, but there's some technical stuff that needs to be worked out still.
Maybe like this is a question I was also asking, like, so you imagine this CCFT as living on the momentum sphere or the spatial sphere?
Spatial.
Spatial sphere?
Yeah.
So, was it possible to do all these derivations in a very spatial way? Like, without ever going to Fourier transforms and so on, right? Maybe I'm just trying to return to this comment you made that it's a collinear and it's occurring in the momentum space.
You know, in fact, maybe I can say something real quick. So this is the second bonus topic, which I won't tell you the answer to, which I won't go through the whole thing of, but I will tell you the answer to. How about this? There's a very spatial way to define these conformal primary operators, which doesn't look like momentum space at all. And how you do this is you have some so-called conformal primary wave function. Okay, I'm gonna write this conformal primary wave function S delta J. S tells you some 4D, this tells you the spin of the 4D particle, okay? Delta is what's ultimately going to be your conformal dimension delta on the celestial sphere, and J is going to tell you the spin of the operator on your celestial sphere. Okay. Now the definition of this so-called generalized conformal primary wave function is it's a function on space-time, x mu, and also a function on the celestial sphere, and it's somehow going to be some maybe Green's function that can allow you to go from space-time to the celestial sphere. So this function, it's defined to be something that transforms as a 4-dimensional spinor tensor field of spin S in the space-time variables and a 2D conformal primary in the ZZ bar variables. I'm not going to get into what this means, but it's something that you can write down and solve. Okay. And the upshot is that you can define conformal primary operators on the celestial sphere by looking at, so if this is some quantum field that lives in 4D, and I take the inner product of this quantum field with the conformal primary wave function, where the inner product will be something like the Klein-Gordon inner product for scalars or some other, or the generalization for spinning particles. Okay, then this is an equally good way to define the conformal primary operators associated to this. This is a space-time field. It's not some annihilation operator. So another way to have treated this subject is to go from this perspective only. And here I don't talk about momentum space at all.
And is collinear limits and so on still tricky, or?
How do you mean?
This commuting collinear limits not commuting.
Yeah. Finding well, at the end of the day, the celestial amplitude is still going to be defined from the momentum space amplitude via Mound transform. So that's still going to be the crucial ingredient.
Maybe I'm asking you this. I said that like in certain theories, when you calculate these correlators, you have these non-local divergences in the momentum space, like 1/k or some divergences. And then when you go to the space, coordinate space, they kind of vanish. So this whole tricky axis of these collinear limits in momentum space and so on. This happens particularly in open field theories and so on. So I was asking that answer that like, is something better, nicer in coordinate space?
I don't know. I mean, I don't know. I guess you could write the scattering amplitude in position space by by Fourier transforming and then do something that looks like a non-transform or whatever. That could be true, but I don't know. I'm not, I don't think there's an answer right now.
Okay.
Yes.
Time was up.
Okay,